Let's look at another example of linear programming. This is about make and buy decisions. Electropoly is a leading maker of slip rings. A slip ring is an electrical coupling device that allows current to pass through a spinning or rotating connection, such as a turret on a ship, aircraft, or tank. The company recently received a $750,000 order for various quantities of 3 types of slip rings. Each slip ring requires a certain amount of time to wire and harness. Unfortunately, the company has 10,000 hours of wiring capacity and 5,000 hours of harnessing capacity, not enough to fill the order by its due date. But the company can subcontract any portion of this order to another company. The following table summarizes the requirements for 3 models of slip rings as well as the unit costs of producing each model in-house and outsourcing. Now let's look at this table. It looks like the customer ordered 3,000 Model 1 rings, 2,000 Model 2 rings, and 900 Model 3 rings. And it takes 2 hours of wiring time for a Model 1 ring, 1 hour of harnessing time for Model 1 ring, and so on and so forth. It is cheaper to make all those rings in-house. For example, $50 for 1 Model 1 ring, $83 for 1 Model 2 rings, and $130 for 1 Model 3 rings. And it's more expensive to buy. For example, $91 for 1 Model 1 rings, and so on and so forth. Electropoly wants to determine the number of slip rings to make and the number to buy to fill the order at the least possible cost. Now let's think about it. We would like to find the decision variables first. What are the decisions involved? And here is the hint. The company wants to determine the number of slip rings to make and the number of rings to buy. And we have 3 different kinds of rings, Model 1, 2, and 3. So we are going to have 6 decision variables. Let's define our 6 decision variables this way. M1 to M3, they are the number of Model 1, 2, and 3 rings to make in-house. And then B1, B2, B3, they are the number of Model 1, 2, and 3 rings to buy from a subcontractor. Now let's look at the objective function. In this case, we are going to minimize the total cost of filling this order. And we know it costs us $50 to make 1 Model 1 ring, and it costs us $61 to buy 1 Model 1 ring, and so on and so forth. So the total cost, or our objective function, is 50M1 plus 83M2 plus 130M3. That's the total cost for us to make the rings in-house. And then plus 61B1 plus 97B2 and plus 145B3. That's the total cost we buy each of those 3 rings from a subcontractor. Next, let's look at our constraints. The first group of constraints is the demand constraints, because customer ordered 3,000 Model 1 rings, 2,000 Model 2 rings, and 900 Model 3 rings. There are 2 different ways of getting those rings. One is to make, the other is to buy. So the total number of Model 1 rings we can provide to our customer is M1 plus B1. And it's going to be exactly 3,000. If this were more than 3,000, it costs us more money. If it's less than 3,000, the order won't be satisfied. So the constraint in this case is an equation. And similarly, we can get demand constraints for Model 2 and Model 3 rings. They are M2 plus B2 equals 2000 and M3 plus B3 equals 900. Next, let's look at our resource constraints. The resource constraints happen only in in-house production. And we know it takes 2 hours of wiring time to make one Model 1 ring, 1.5 hours to make one Model 2 ring, and 3 hours to make one Model 3 rings. So the total number of hours of wiring time needed in-house is 2M1 plus 1.5 M2 plus 3 M3, which should be no more than the availability, 10,000 hours. Similarly, the total number of harness hours needed should be no more than availability, 5,000 hours. It's going to be 1 times M1 plus 2 M2 plus 1 M3, which is less than or equal to 5,000. Last but not the least, non-negativity constraints. We want all of those 6 decision variables to be non-negative. Okay, now we're ready to move on to Excel. I'm going to show you how to solve this model in Excel using Solver. Here's my Excel spreadsheet. I've already prepared some basic information. Let's take a look. For example, here is our decision variables. Number of Model 1 rings to make, number of Model 1 rings to buy, and so on and so forth. These 6 decision variables are in cell B6 all the way to D7 in my spreadsheet. Next part of this model is the unit cost to make or buy each unit of Model 1, 2, and 3 rings. They are in my cell B10 all the way to D11. This is just one way to arrange your information in Excel spreadsheet. There are different ways you can do that. Whichever way works for you, it's going to be okay. Now let's pay attention to our objective. We would like to minimize the total cost. How do we get that? We know from our linear programming model, it's going to be 50 times M1 plus 83 times M2 plus 130 times M3 plus 61 times B1 plus all the way to 145 times B3. And here I'm going to show you a much faster way of formulating objective function in Excel. The function we're going to use is called sum product. S-U-M. P, here it is, sum product. Let's double click. Sum product of what? Actually 2 matrices. One is our decision variable matrix. The other is our coefficient matrix. Close the parentheses and we're done. Sum product does nothing but what I said earlier. It is nothing but 50 M1 plus 83 M2 plus all the way to 145 times B3. And right now, because all those decision variables by default are 0, the total cost is also 0 over here. But once we get the optimal solution over here, we're going to get our lowest possible cost, or our optimal cost. Next, let's formulate constraints. The first one is the demand constraint. In cell B13, I'm going to come up with how many Model 1 rings we can provide to our customer. It's coming from M1 plus B1. Okay. In Excel, in my case, it's B6 plus B7, which should be equal to 3,000. And we're going to do the same thing for Model 2 and Model 3 rings. In Excel, I can just drag, copy, and paste the formula for C13 and D13. For example, if you look at D13, what's the formula? It's going to be D6 plus D7, or our decision variable M3 plus B3. That's the first group of constraints. The other is resource requirements. Let's see how many hours of running time we're going to use. It's equal to 2 times M1 plus 1.5 times M2 plus 3 times M3. And once again, for convenience, I'm going to use the Excel function sum product. And this time, the two matrices are 1/3 matrices. It's going to be from cell B18 all the way to D18 times what? Number of model 1, 2, and 3 rings we are going to make. Be careful, we're going to need wiring hours only if we do that in-house. And here I'm going to use something called absolute cell reference. And by adding $signs, why do we do that? It does not affect the formula in cell E18, the total number of hours of wiring time we're going to use. But the thing is, we're going to copy and paste the formula. And if you look at E19, what are we going to do? 1 times M1, 2 times M2, 1 times M1, and add them up, right? So what do we know? We're going to keep referring back to M1, M2, M3. In our Excel, there are cell B6 all the way to D6. And that's why over here, I tried to add $signs to fix the cell B6 all the way to cell D6. That way, when I copy and paste the formulas, those will remain the same. Okay, let's give it a try. Here we go. Let's take a look. You see, in the cell E19, first part of sum product formula, B19 to D19, that's what we want, right? Because now we're talking about harnessing hours. So the coefficients are different right now. They are 1, 2, and 1. So that's supposed to be different, right? And the second part of the formula, well, we don't want to change that, right? We still want to use M1, M2, M3, or those are cell B6, C6, and D6. That's the purpose of adding $signs, called absolute cell reference. All right, now we're ready to solve this model by launching and using Solver. I have my Solver installed already. It's under Data tab right here. I'm just going to click it, Solver. And this time I'm using 2010 version of Excel, so the Solver parameters look a little bit different. But they do the same thing as the 2007 version of Solver. First of all, what's going to be our objective is minimizing the total cost, right? Total cost in our case is in cell E11. Let's just click it. And be careful over here, because it's cost, we would like to minimize it by doing what? By changing the values of M1, M2, M3, B1, B2, B3. Those are in cell B6 to D7. Let's just highlight it. Next, let's add constraints. Let's click Add. First, let's add demand constraints. Number of model 1, 2, and 3 rings will be equal to the number ordered. That takes care of the demand constraint. We're going to click Add because we have another group of constraints to add. And that is going to be the resource requirement. Okay, what do we have? Number of wiring hours and harness hours used should be less than or equal to or no more than their availability. They are 10,000 and 5,000 hours respectively. Now we're done with all the constraints, and we can just click OK. You may wonder, what about the non-negative constraint? That's okay. We can take care of that right here. Let's take a look. You see, make unconstrained variables non-negative. We just need to check this box. That way we make sure M1, M2, M3, B1, B2, B3 to be non-negative. Another thing I want to bring to your attention is select a solving method. We're going to choose simplex LP method. That's it. We're ready to go. One last thing for us to do is just click solve. Okay, now we got our optimal solution and optimal cost already. Let's go ahead and keep the solver solution. Okay, let's take a quick look at the result. What do we find? Okay, we're going to make all the 3000 Model Y rings in-house. Similarly, we're going to make all the Model 3 rings in-house. And next, we're going to make as many as Model 2 rings in-house. But because of resource constraints, we can only make 550 Model 2 rings in-house. That is to say, we have to outsource. By subcontracting, we're going to buy 1,450 Model 2 rings from subcontractor. What do we get? The total cost comes out as $453,300. Keep in mind, the value of this order is $750,000, so we're making a pretty decent profit.